discussion like this, no? F is equal to NV by, so 2n minus 1 V by 4L. We'll agree this. What is V? V is the speed of sound where in a medium that is filled up in a particular pipe, that one. And what is L? L is the length of the pipe. And what are all the V and L were kept constant. As I increase N, the F was increasing. Am I right? Yesterday's discussion. Okay, let's see now. Let's bring another situation where if I keep F constant, then as N varies, L will also vary. Can be a situation, no? So there's what the first case. What is the first case is like V and L were constant. Second situation I'll bring where F will be constant. F and V will be constant. Then N and L will be varying. I can also bring a situation where the V and L can change. Very difficult. Okay, these are the two very popular things are there, which will focus here. So actually what happened, we had a discussion, theoretical discussion on this aspect, where the speed of the wave in organ pipe was constant, length of the pipe was constant. Then as N increases, F increases. Now, so F is maintained constant, then V is constant. Anyway, V will be constant. So as I vary the length of the pipe, N is going to change. So this is called like a resonance air column. This experiment is called as this. I'll use this to determine the speed of sound in air. I'll bring another one. I'll fill up liquid in a cylindrical pipe. So here the tuning fork. Okay, how the tuning fork? Lateral lateral. So there's a water, and I have here a tap where I can control the amount of water in that particular thing. So what is this? There's a cylindrical pipe, glass pipe, water. So I'll take the tuning fork. I'll vibrate. I'll strike it against rubber cord. I'll keep it here now. So as it starts vibrating, as the tuning fork starts vibrating, the air here will be pushed. So the vibration, the sound wave will be generated, and the sound wave starts moving here now. I will decrease the level of water. Then what I notice is like as the level of water decreases, and at one particular level, I'm going to get a maximum sound. Why maximum sound? Because tuning fork will act like a source. the tuning fork will act like a source of sound signal. And what do we get? I'll get a maximum sound at one particular length here. The reason for that, when do we get maximum sound? At resonant frequencies. So the length of this will be such that L1 you put it. So here, let me talk, this is a displacement wave. So how do this will behave? Open it, and this will the layer of water. This part is air, no? This is air, no? And this is water. Air column it is, and this is a water column. Now this part is what happened air column. So when the length of air column becomes equal to resonating length, I'm going to get a maximum sound. So sir, how the sound will be? I think all of you, I told you yesterday to blow some air in a pipe, in a pen cap, the way you get sound, no? The similar sound what you are going to get here. Nobody is blowing air here. Just if you keep vibrating tuning fork here, you are going to get the maximum sound. So here, maximum sound is earth. Let me put that tab. Otherwise, you'll think how that level has decreased. Okay, maximum sound is earth. Here also maximum sound is earth. In between, we don't get. So next again, the same vibrating tuning fork will be there. What are this? This is the air particles here. They'll be vibrating here. Then continuously tuning fork will be vibrating. Continuously I'll get incident wave, continuously reflected wave. The superposition of that, what happened? We'll get a standing wave. And when do we get maximum sound? When the length of air column becomes equal to resonating length here. So what is this distance? We can write it as, we know this should be lambda by 4. Distance between antinode, there's a displacement antinode, this is a node. Antinode, node. What can be this? Same lambda by 4. And what about this? Lambda by 2. I'll measure this length. I have a scale. I'll measure that corresponding length here. Now, what is the vibrating tuning fork? Strictly, it is not just tuning fork. It's a vibrating tuning fork. Getting this one, I'll decrease the level of water. As the level of water, once the length of air column becomes equal to L1, I'm going to hear a maximum sound. Then again, in between, I'll get a sound, but not maximum sound. In between also, I'll hear sound, but will not be maximum. Then again, when the level of water becomes equal to exactly L2, again, I'm going to hear a maximum sound. So in this way, what will happen? So we will get a some resonance particular thing. So who is a source? The tuning fork is a source which will supply energy. And we will accept that the air column. So when the maximum transfer of energy from tuning fork to air column will occur, when the frequency of tuning fork becomes equal to resonant frequency of air column, here resonating length of air column. Okay, what is our question? We have to find out the speed of the sound in this air, no? What is the formula for that? Okay, first let me go for what is L1 lambda by 4. What is the length? L2 is equal to lambda by 4 plus lambda by 2. So this should be equal to 3 lambda by 4. Do I know L1, L2? Yes, L1, L2 are measurable. I do have a scale. Happily, I'll measure the length L1, L2. Then let me take L2 minus L1. 3 lambda by 4 minus lambda by 4. This should be equal to how much? Lambda by 2. What is lambda? V by 2f. V by f, lambda is. Then what we are having? E equal to 2f L2 minus L1. So what is this? Speed of sound. It's I know frequency of tuning fork. I know L2 and L1. I'll measure. So when do maximum sound is heard? Only when the length of air column is equal to resonating length. These L1, L2 are called as resonating length. So I'll decrease further the level of water. I'll get one more. I'll get one more. I'll get one more. Like that, what happened? The keep on, we can keep on decrease the level that one. So I don't have space here. So one more, sir, what will happen next? Again, you'll get two end of loop. That resonating length will be L3. So shall we put it like a consecutive? So here don't think that off loop, then two end of loop will come. After the off loop, one end of loop. After this, two end of loop will come. So the next resonating length will be I think better let me adjust here only. Okay, there's a tap. No, what is the next resonating length? So this length will become L3. Okay, what is L3 should be equal to? 5 lambda by 4. So I don't have space here. I'll write it here. Lambda by 4, lambda by 2, lambda by 2. Like that, I'm going to keep on here a maximum sound only when the length of air column is equal to resonating length. There's a meaning of this one. Maximum sound is earth. Okay, all of you, very simple. Sir, in between, when the length of air column is between L1 and L2, do I hear sound? You are going to hear a sound, but will not be maximum. I think as it starts approaching, then what happens? So somewhere here, so like suppose L1 20 centimeter, L1 5 centimeter, no sound will come. As the length of air column approaches L1, the sound will increase exactly at L1 maximum sound. Again it decreases, and somewhere here what happen? Hardly we may get sound. Again what happen? Again we'll get a sound increases, then again maximum. So I'll put it simple, that one. As the length of air column, no, 0, no sound. Then sound output starts increasing. Maximum sound. Fine. Next again, it starts decreasing. Then almost no sound. Then again sound starts increasing. Maximum sound. Then start decreasing. No sound. Again, it starts increasing. Maximum sound. So we are more interested in the resonating length, where I'll get maximum. So how do I come to know maximum sound I'm going to hear? That's what it will be. It's not that here what when it starts increasing, here you're going to definitely say that maximum sound you can hear. Very next moment, as the length of air column increases, it start decreasing. So like this, what happen? You have to repeat experiment 1-2 times and exactly note down that resonating length. Got the idea now? Okay, there's a one background is what you needed here. It's a very famous numerical. So many times they've asked student has to just remember the conditions here, nothing big. Any doubt if you have, you can clarify. Okay, no, so we'll take the next. Yesterday I asked you to think on how the reflection at open end usually that occurs. Okay, let's give me a better example. Okay, now the compression I'll just show it.